Radical expressions and functions. Square roots. The square root of a number is one of its two equal factors. Here's an example. The square root of 36 is 6, since 6 times 6 equals 36. The square root of 36 is also negative 6, since negative 6 multiplied by negative 6 equals 36. So 36 actually has two square roots, 6 and negative 6. However, we're only going to be concerned with what's called the principal square root. The positive square root is called the principal square root. We will mainly be concerned with the principal square root. Here's a symbol for the square root. You should be able to find that on your calculator. You could actually type in the square root of 36 on your calculator and it will give you 6. It gives you an integer because it's a perfect square. If you typed in a number like 15, square root of 15 is not a perfect square. You'll have to approximate that by rounding. Okay, so this symbol is called a radical sign. Kind of almost looks like a division box, but with a check mark at the end. So it is used to designate the principal square root. So if you were to type in square root of 49 on your calculator, you would get 7. And that's because square root of 7 times 7 is 49. Square root of 81 is 9, because 9 times 9 is 81. So just when you read it, it's read as the square root of 49. The number under the radical symbol is called the radicand. So in these examples, 49 and 81 are the radicands, radicand. And the symbol is called a square root. In general, it's called a radical sign. This one's a square root, but in general, they're called radical signs. Here's some examples. So what we're looking for is the number multiplied by itself that gives you the radicand. You might want to pause the video and work it out. Okay, square root of 121, what times itself is 121? That would be 11. How about the square root of 0? What times itself is 0? Right, 0. Square root of negative 25, what times itself is negative 25? And there is no number. I should say there's no real number. So that's what we'll say right now. It's not a real number. We will talk about this later in the chapter when we talk about complex numbers or imaginary numbers. So just kind of hold off on that. But for right now, the square root of negative 25 is not a real number. How about this fraction, 25 over 49? The square root of 25 over 49. What times itself would give you that fraction? Well, we can also just look at it individually. What's the square root of 25? 5. What's the square root of 49? 7. So the answer would be 5 over 7. Last one here, the square root of 144. That would be 12. 12 times 12 is 144, but there's a negative sign in front, so just leave the negative sign in front of your answer. Okay, we're going to talk about cube roots now. The cube root of a number is one of its three equal factors. Here's the symbol for cube root. It almost looks like a square root, but there's a little 3 inside that check mark area. That 3 designates the cube root of a number. Here's a couple of examples. The cube root of 8 is 2, because 2 times 2 times 2 equals 8. How about the cube root of a negative number? We can have the cube root of a negative number. In this case, it's negative 5, because negative 5 times negative 5 times negative 5 equals negative 125. Again, you read this as the cube root of 8 is 2, and the cube root of negative 125 is negative 5. So it's important to note that the radicand of a cube root can be negative, but the radicand of a square root cannot be negative. If it is negative, the answer is no real number. If a cube root has a negative radicand, then the answer will just be a negative number. All right, A, cube root of 27. What multiplied by itself 3 times is 27? Again, you should always pause the video and try to work it out. So the answer is 3. How about the cube root of negative 64? Negative 4, because negative 4 times negative 4 times negative 4 will equal negative 64. In part C, we have a fraction. You might want to think about the numerator and denominator separately. What is the cube root of 8? 2. What is the cube root of 125? 5. So our answer is 2/5. Okay, cube root of 343. This might take a little bit of work. You know, it's got to be bigger than 5, because 5 times 5 times 5 is 125. So you might want to take your calculator out and try to see if it's 6. 6 times 6 times 6. And maybe that doesn't work. So then you try 7 times 7 times 7, and that's it. There is also a cube root button on your calculator. It should be right above your square root button. You might have to hit the shift first. So look for the cube root button on your calculator. It looks like that looks like a square root, but a 3 inside the check mark. Okay, so you should be able to type that into your calculator, or if you just guess a little bit, it's going to be 7. Oh, since there's a negative in front, the answer should be negative 7. Okay, thus far we have covered square roots and cube roots, but there are also nth roots, fourth roots, fifth roots, sixth roots, etc. Here are some examples. On the left there we have square root of 121. Below it, cube root of 8. Below that, the fourth root of 81. So that's how you say it, fourth root of 81. On the right, we have the fifth root of 32. And below that, we have the sixth root of 15,625. The numbers which designate the root is called the index number. The index number for the square root is a 2. However, it is usually not written. It's just assumed, so you don't have to write the little 2. If you want to, you can. But when it's not written, it's assumed to be 2. Here's our definition. The nth root of b equals a if and only if a to the power n equals b. So that's saying that we're looking for the number raised to the nth power to give us a number that is the radicand. Or what number multiplied by itself n times will give you the radicand. So example 3, part 8. The fourth root of 81. What number raised to the fourth power will give you 81? Or what number multiplied by itself 4 times will give you 81? It may take some work, maybe play on the calculator a little bit, but you should end up with an answer of 3. 3 to the fourth power equals 81. Or 3 times 3 times 3 times 3 equals 81. Okay, how about the fifth root of 32? What times itself 5 times is 32? Or what number raised to the fifth power equals 32? And that number will be 2. How about our last one? Has a 5 at the end. I would try 5. So on your calculator, type in 5 to the 6th power, or write down 5 times 5 times 5 times 5 times 5 times 5, 6 of them, and you should get 15,625. So the answer is 5. Okay, we're going to talk about square roots of variables that are perfect squares. So here we wrote square root of 36 equals 6 because 6 times 6 equals 36. So let's look at our first example there, square root of x squared. What times itself is x squared? Right, x. X times x is x squared, so the answer should be x. You're almost right, but we have to put the absolute value around it. And that's because we don't know whether x is positive or negative. Remember that we talked about the principal square root. The principal square root of 36 is 6, not negative 6. Even though negative 6 multiplied by negative 6 is still positive 36, we only want the principal square root. We want the answer to come out positive. So because we don't know if x is positive, we have to put an absolute value sign around it. Okay, in the future, we won't worry about the absolute value because we're going to assume that the variable is a positive. But for right now, there is no instruction that says we could assume it's a positive variable. So we need to put an absolute value around the x. That makes it positive. How about the square root of x to the fourth? The answer is x squared, because x squared times x squared is x to the fourth. Now, why did I not put an absolute value sign around it? Well, because when you square x, squaring anything, even if it's positive or negative, the result will be positive. So therefore, we're not going to get a negative number from that result. So we do not need to put the absolute value symbols around it. How about our next one? The square root of x to the sixth. The answer will be x to the third. However, when you cube something, if it's negative, your result will be negative. So this one, we need to put an absolute value symbol around it. Okay, let's keep going, and then we'll read those two observations on the right. The next one is x to the fourth. We do not need an absolute value symbol around it because anything raised to the fourth power is positive. And the last one, what times itself is x to the 10th? X to the 5th. Again, you need an absolute value symbol around it because anything to the 5th power, if it's negative, will still be negative. So let's read these observations. The square root of a variable with an even exponent equals the variable with an exponent of half of the exponent in the radicand. So looking at all these problems, they were all even, right? 2, 4, 6, 8, and 10. The answer was an exponent that was half of that, or dividing it by 2. So 6 divided by 2 is 3. 8 divided by 2 is 4. So that's another way you can see it. Divide the exponent of the variable inside the radicand by 2, which is the index number. The second observation is that the answer of a square root needs the absolute value symbols only when its exponent is odd. So when did we need an absolute value? When the exponent of the variable was a 1 or a 3 or a 5. We'll expand that observation in general, but for right now, the square root only needs an absolute value when its answer is a 1, a 3, or a 5, or any odd exponent. Let's talk about cube roots. Now, let's look at these past problems. The cube root of 8 is 2, because 2 times 2 times 2 is 8. And the cube root of negative 8 is negative 2. We can have a negative for an answer if the index is 3. So therefore, we will not need any absolute values to keep it positive. The first one would be x, because x times x times x is x to the third. The second one, what times itself 3 times is x to the 6? That would be x squared. So let's read these observations to the right before we finish the last two. The exponent of the answer is equal to the exponent of the variable in the radicand divided by the index number. So looking at that, does that make sense? 3 divided by 3 is 1. 6 divided by 3 is 2. The next one should be 9 divided by 3, which will be 3. And how about the last one? 12 divided by 3, 4. That second observation, the absolute value symbols is not needed for cube roots. They are only needed, so this is a general statement, they are only needed when the index is even and the answer has a variable with an odd exponent. So they're only needed if the index is even, so for square roots, fourth roots, sixth roots, and the answer has to have a variable with an odd exponent. Okay, let's do some radical expressions here. Square root of x to the 16th. Our index is 2. So the easiest way to think about it is to divide 2 into 16. That should give you x to the 8th. No absolute value needed because our exponent is even. How about our next one? 2 into 30 is 15. That's an odd exponent. Absolute value needed. Our next one, 2 variables this time. So 2 into 12 would be 6, and 2 into 20 would be 10. No absolute value needed because both exponents are even. Let's go on to example 5. 2 into 10 would be 5, and 2 into 4 would be, 2 into 8 will be 4. Oh, absolute value needed around the x to the 5th because it's an odd exponent. So these symbols show that we're trying to make the x to the 5th positive. If you were to put absolute value around the whole thing, it wouldn't be harmful. It's just not necessary, but it just shows that why we're using the absolute value is because of the x to the 5th. But if you put the absolute value around the whole expression for your answer, it would not be wrong. Okay, the next one, this one has a number also, square root of 9x to the 4th. So we need to do the square root of 9, which is 3. And then 2 into 4 would be 2. So 3x squared. Okay, so when we have a radical expression, we take the square root of the number first, and then divide each exponent by 2, because the index is 2. Okay, square root of 36 is 6. 2 goes into 14 7 times, and 2 goes into 22 11 times. So this one needs absolute values around the x to the 7th and the y to the 11th. So therefore the whole thing is inside an absolute value. The 6 is not. If you included the 6 inside, again, it wouldn't be harmful. It's just probably not traditional to put the 6 inside the absolute value along with it. Okay, some cube roots. Now again, remember that the absolute values symbols are not needed for odd roots. They are only needed when the index is even. In this case, our index is 3, so our index is not even. And the answer has a variable with an odd exponent. So again, we don't have to put any absolute values because our index is odd. In example 3. When we go on to example 7, I think I said that wrong. For example 6, all of the index numbers are 3. But when we move on to example 7, our index numbers are 4 and 5. So we may need the absolute values for parts A and B, not C and D though. Okay, so the first one, the cube root of x to the 15th. So we could figure out what times itself 3 times is x to the 15th. Or the shortcut is to divide the exponent inside by the index. So 15 divided by 3 is 5. Now we move on to the next one. 30 divided by 3 is 10. 12 divided by 3 is 4. X to the 10th, y to the 4th. Part C, the cube root of 125 x to the 18th. So first we need to figure out what the cube root of 125 is. What times itself 3 times is 125? Or what to the 3rd power is 125? And that answer would be 5. And then divide 18 divided by 3, which will be 6. So 5x to the 6. Okay, next one. We have a negative 64. So what's the cube root of negative 64? That would be negative 4. So whenever we have a negative, our cube root will also be negative. Negative 4 times negative 4 times negative 4 is negative 64. And then divide the index into each of the exponents inside the radicand. So 3 goes into 21 7 times, and 3 goes into 33 11 times. So negative 4 x to the 7, y to the 11. 7, 11. Yep. Okay, example 7. Same concept. Part A is a 4th root. So we're going to divide 4 into 20. 4 goes into 25 times. But we need to put the absolute value because our answer is odd. Next one. 4 into 32 and 4 into 40. So that will be x to the 8th, y to the 10th. No absolute values are needed because each exponent is even. Part C, 5 into 35 will be 7. No absolute value needed because the index is odd. And part D, 5 into 25 is 5. 5 into 50 is 10. Again, no absolute value needed. Okay, some more examples. Part A, the fourth root of 81. What raised to the fourth power is 81, or what multiplied by itself 4 times is 81? That would be 3. And then 4 divides evenly into 28 7 times. So 3x to the 7th, with the absolute values around the x to the 7th. Whenever our index is even and our answer has a variable that's odd, that's when we need the absolute values. So here's our note. The absolute value symbols is not needed for odd roots. They are only needed when the index is even, that's what we have, and the answer has a variable with an odd exponent. Okay, part B. Fourth root of 16. That would be 2, because 2 to the fourth is 16. And then divide 4 into 44 and 4 into 12. You get 2 times x to the 11th, y to the 3rd, and the x and y must be inside the absolute value because the index was even and the answer has odd exponents. For parts C and D, we will not need absolute values because our index is not even. Fifth root of 32, that would be 2. And then 5 divided into 45 would be 9. Fifth root of negative 32, that would be negative 2. Negative 2 raised to the 5th power would be negative 32. And then divide 5 into 20 and 5 into 10. So our answer is negative 2 x to the 4th, y to the 2nd. Example 9. We have a 6th root of x to the 12th. Part B is also a 6th root. Part D is a square root. So for A, B, and D, we may need the absolute values if our answer has an odd exponent. Okay, in A, divide 6 into 12. That'll give you 2. So we do not need an absolute value because our index was even, but our answer was also even. Okay, part B, 6th root of 64. That would be 2, because 2 to the 6th power is 64. And then divide 6 into 42, that'll give you x to the 7th. Oh, that's an odd exponent. Therefore, we need absolute values. Part C, we will not need an absolute value because the index is 7. So divide 7 into 35 and 7 into 21. X to the 5th, y to the 3rd. Part D, the square root of x plus 5 squared. So this was a little bit different because it's a binomial. It'll come up again later in this chapter when we're solving equations with square roots. So what times itself is x plus 5 squared? And the answer will just be x plus 5 to the first power, so we need to have the absolute value around it to make it positive. Okay, so if that was x plus 5 to the 4th power, then our answer would be x plus 5 squared, and we would not need an absolute value. If it was x plus 5 to the 6th power, the answer would be x plus 5 to the 3rd, and we would need an absolute value around it. Okay, let's move on. Okay, we're going to talk about radical functions now. A radical function is any function that contains a variable inside a root. We will mainly cover square root functions and cube root functions. Here's a couple of examples. F of x equals the square root of x plus 6. Notice that there is a variable inside the square root. And the second one listed to the right is f of x equals the cube root of 3x minus 5. Again, there is a variable inside the cube root. The first one on the left is called a square root function because it's a function and it has a square root. What do you think the one on the right is called? It's called a cube root function because it is a function and it has a cube root. We're not very imaginative, are we? Okay. Example 10. F of x equals the square root of x minus 2. First, we'll find f of 3. That means everywhere you see an x, replace the x with 3. So f of 3 equals the square root of 3 minus 2. Simplify the radicand. 3 minus 2 is 1. And then the square root of 1 is 1. So f of 3 equals 1. Part B, let's find f of 11. So everywhere you see an x, replace x with 11. So 11 minus 2, simplify that, that'll give you 9. And then the square root of 9 is 3. So f of 11 equals 3. Part C, f of 1. Everywhere you see an x, replace it with 1. Simplify the radicand. 1 minus 2 is negative 1. And can we have the square root of a negative number? No. So the answer is no real number. Again, we'll discuss non-real numbers at a later section. That section will be called complex numbers. All right, let's work on a cube root function this time. Part A, find f of 9. So everywhere you see an x, replace the x with 9. So 9 minus 1 underneath the radical sign. That'll give you an 8. The cube root of 8, that would be 2. So f of 9 equals 2. For part B, let's find f of negative 7. So everywhere you see an x, replace it with negative 7. Negative 7 minus 1 is negative 8. We can have a negative inside a cube root. That'll give us a negative 2. If that was a square root function, we would say no real number, but it's a cube root, so we can have a negative in a cube root. All right, last one, f of 2. So wherever you see an x, replace the x with 2. 2 minus 1 is 1, and the cube root of 1 is just 1. 1 times 1 times 1 equals 1. Okay, now we're going to talk about domains. First, we'll talk about domains of square root functions. So it's important to note that we cannot have a negative number in a square root. The square root of a negative number is not a real number. It's called an imaginary or a complex number. And again, we'll cover complex numbers at a later time. So here's our procedure for finding the domain of a square root functions. It's actually also the domain of even root functions, but we'll talk about that again later. So step 1 is set the radicand. Again, what is the radicand? The radicand is what is underneath the radical sign. We're going to write the radicand greater than or equal to 0 and then solve the inequality. Then step 2 is we're going to write the solution in interval notation. It doesn't say to graph, but whenever I'm writing an inequality in interval notation, I think it's always a good idea to graph it first and then write it in interval notation. Okay, here's our first problem. Find the domain of f of x equals the square root of x. Okay, so this is probably the simplest square root function that we could write because the only thing underneath the radical is an x. So our step 1 is to write the radicand greater than or equal to 0 and solve the inequality. So our radicand is x, so we're just going to write it greater than or equal to 0. Now it says to solve, but there's nothing to solve. X is already by itself. So let's make a graph. Put 0 on a number line, and then which way would we shade? X is greater than or equal to 0. We would shade to the right. And we would use brackets because it has the equal symbols. So then writing that in interval notation would be brackets 0, comma, infinity. Okay, so these are the numbers that you could insert for x in the square root function and get a value that's not a complex number or not an imaginary number or not a non-real number. So you could plug in 9. Square root of 9 is 3, but you cannot plug in negative 9. Square root of negative 9 is a non-real number. Now you might have to use your calculator to evaluate some of these, like if you plug in 5, x equals 5. The square root of 5, if you type that into your calculator, now some calculators will just leave it as square root 5. There's an SD button on your calculator, on the Casios. It'll round it to a decimal, 2.236067977. So if we rounded that to the 10th, it would just be 2.2. So you might have to use your calculator to get some of these numbers, but you can still do it. If you plug in the square root of negative 5 on your calculator, it should say math error, maybe not possible, something like that. Okay, let's go on to the next one. Find the domain of f of x equals the square root of 2x minus 5. So again, write the radicand greater than or equal to 0 and solve the inequality. So the radicand is 2x minus 5. So write 2x minus 5 greater than or equal to 0. Now get x by itself. How would we get x by itself? Right, add 5 to both sides. So that gives us 2x is greater than or equal to 5, and then divide by 2 on both sides. So that gives us x is greater than or equal to 5 halves. Again, I would graph this first. Just put 5 halves right in the middle. And then which way would we shade? Yes, we would shade to the right, and we would use brackets. Now writing that in interval notation, that would be brackets, 5 halves, comma, infinity. All right, finding domains of cube root functions. This one's a lot easier. You'll like it. We can have a negative number in a cube root. Therefore, the domain of a cube root function is simply all real numbers. Or in interval notation, parentheses, negative infinity, comma, infinity, close parentheses. So here's example 14. Find the domain of f of x equals the cube root of 3x minus 2. There's simply no work to do. Since it's a cube root function, the domain is all real numbers. You could write all real numbers if you want, or you could write it in interval notation. It depends on the directions on a homework assignment or on a test. So you could write the words all real numbers. There's also a symbol for all real numbers. It looks like an R, but with two vertical lines instead of one vertical line. Okay, let's go on. Finding the domains of nth root functions. So we talked about square roots, we talked about cube roots. Let's generalize this. If the index number is even, we cannot have a negative number in an even root. Therefore, we follow the same procedures as finding the domain of a square root function. So if the index is a 2, or a 4, or a 6, or an 8, it's the same procedure. We set the radicand greater than or equal to 0, and then solve the inequality, and then we write the solution in interval notation. If the index number is an odd root, we can have a negative number in an odd root. Therefore, we follow the same procedure as finding the domain of cube root functions. What is that procedure? There's nothing to do. The answer is all real numbers. So odd roots, the domain is all real numbers. Even roots, greater than or equal to 0, and solve. Almost done. Okay, here's example 15. Find the domain of f of x equals the fourth root of 3 minus 2x. Okay, it's an even root, so write the radicand greater than or equal to 0. So that's 3 minus 2x greater than or equal to 0. Now we need to get x by itself, so subtract 3 on both sides. That gives us negative 2x is greater than or equal to negative 3. Now divide both sides by negative 2. Oh, hope you remember, when you divide by a negative, what do you have to do? Right. You have to flip it, right? You have to reverse the inequality symbol. Whenever you divide both sides by a negative, you must flip the inequality symbol. So x is less than or equal to 3 halves. Okay, let's graph it. Put 3 halves in the middle, and this time, which way would we shade? We would shade to the left and use brackets. So then writing that in interval notation, it would be negative infinity, comma, 3 halves, brackets. All right, example 16, last one. Find the domain of f of x equals the fifth root of 7 minus 5x. The index number is odd, so the domain is simply all real numbers. Negative infinity to infinity inside parentheses. All right, that's it for this video. I'll see you here for the next one.